And basically an Hermitian form. So what's an Hermitian form? It's a function, right, from the product of two copies of a vector space over C to the field of complex numbers C, which satisfies certain properties, namely it is linear with respect to the first factor, right, to this one. And well, it is antilinear in general, so antisymmetric in general, right? Antisymmetric in general, meaning that h of, say, xy, x comma y, is the same as h y x bar, where bar is the complex conjugation, right? By the way, if you restrict yourself to real numbers, so if you just let your Hermitian form, so if you let your Hermitian form just be defined on real numbers, then it's clear that conditions 1 and 2 transform into the conditions for being a symmetric bilinear form, right? Because if say in condition 2, if all numbers are real, then we know that the conjugate of a real number is the same number. So basically it would mean that h of x comma y is the same as h y comma x, if x and y are reals, right? Okay, so in other words, the concept of an Hermitian form is a generalization, if you wish, is an extension of the concept of a symmetric bilinear form to complex numbers, right? And last time we produced a couple of examples, and well, there was an important example which was dealing with inner product. Again, let me stress that inner product is an example of an Hermitian form, right? So to get an inner product, one just needs to have conditions 1 and 2. And, well, the third condition, which is just saying that the third condition, which is saying that if, say, vector u is non-zero, then if I apply this Hermitian form to the same vector, to the same vector u, I'll get something which is strictly greater than 0. Again, this condition totally makes sense because, as we have seen, if you apply your Hermitian form to the same vector, you'll get a real number, right? So it totally makes sense to compare this real number with 0. Okay, so that was an inner product. And again, last time we introduced a couple of properties, right? We introduced several examples of Hermitian form. So let me now, we also introduced a couple of examples of inner products. So let me again mention it. There is, of course, a very basic and motivating example for the inner product, namely the standard example, the standard inner product. Now let me remind you what's this. So you just need to take your vector space to be just Cm, okay? And then, well, your inner product is just defined by the same formula as the standard Hermitian form. So standard Hermitian form is the inner product, right? So x comma y is just set to be, if you set, say, x to be this vector, x1, xn, and y to be this vector, y1 to yn, then this is just what? This is just a sum of products, right, of coordinates xi times yi bar, right? So that was a inner, this was a standard inner product. Okay. By the way, yeah, let me just check condition 3. Check 3 in this case. What will happen if we try to compute x comma x? Well, by the formula, we will get what? We'll get a sum from 1 to n of xi times xi bar. Don't forget that each xi is a complex coordinate, right? And now, well, if you remember, the basic property of the complex numbers of the conjugate is that if you take a complex number and multiply it by its conjugate, what do you get? You get the square of its absolute value, right? Yes. So basically, what do you get? You just get the sum of squares of its coordinates. So let me maybe mention. So what you will get something like this, right? So let me remind you that the absolute value of z is what? It's square root of a square plus b square, where z is written as a plus ib. Okay. Is there any question so far? Any questions so far? Yeah. So that was an example of a standard inner product. This was an example of a standard inner product. Well, actually, this is an example of an inner product, and this is a standard example, right? So that's, so if someone asks you, give please an example of an inner product, so that's it. That's the basic example. Okay. However, there are a bunch of other examples, and well, let me just mention another one, which is also pretty important, of an inner product. And this one also is pretty important, and it appears at it's actually has is very important in applications, say in physics and engineering or whatever, and it deals with functions. Right. On the vector space of functions, you can also introduce the Hermitian form. You can also introduce and the inner product. So how do we do this? Well, okay. So let's say take V to be the vector space of all complex valued functions, of all complex valued functions. We have seen this already many times, right? For instance, we know that this is infinite dimensional space, right? And well, say, okay, so in this vector space, each function, like trigonometric function or exponential function, plays a role of an abstract vector, right? Okay, so now, well, let's just, let's restrict ourselves to the space of all continuous complex valued functions. Moreover, all continuous complex valued functions on a certain specific interval, namely on the interval from 0 to say 2 pi. Okay. Then what we can do, we can just define, well, let's just define the following function. So that form, so this is just, so the form applied to the vector f comma to the vector f comma vector g is said to be the following. You take 1 over 2 pi of the integral from 0 to 2 pi of what? Of the product of ft, gt bar, don't forget that these functions are complex valued, and then dt. And indeed, one may check, well, it's pretty straightforward to see that this form is indeed, well, first of all, this is clearly an Hermitian form, but moreover, this is indeed an inner product. Is an inner product. Okay. And right, so it's pretty easy to see, it's pretty easy to check condition 3. Right? Why? I mean, say, for instance, what is f comma f? What is f comma f? Well, this is by the very definition is the following integral. So from 0 to 2 pi of what? Of ft bar, right? dt. But then you can obviously simplify it, what do you get? 1 over 2 pi, the integral from 0 to 2 pi of what? What is ft times the conjugate of ft? Ft is a complex number. So complex number times its conjugate is the square of its absolute value, right? So I just put it here like this, ft squared dt. But then, look, I mean, this function is non-negative, right, on the intervals from 0 to 2 pi. And one of the basic properties of the integral tells you that if you take the integral of a non-negative function on the interval, then you will get a non-negative number, right? So first of all, let me mention that, right, so let me maybe stress that this condition, we are checking this condition, right? So, so now we know that, so if, say, f of t is greater or equal than 0, then clearly f of f is greater or equal than 0. But moreover, we can say that, well, I mean, if your function is really, say, is strictly greater than 0 at certain point, so it's continuous function, right? So if f of t is greater than 0 for some t on this interval, then again, by the property of the integral, one checks that, well, one gets that this integral then will be strictly positive. Okay. That means that the property 3 is, well, it really holds in this case. Okay. Right. Well, there are plenty of other examples, so let me also mention the following one. Well, remember that there was an example of an Hermitian form for matrices, right? Remember that was H from Mn of C times Mn of C to C, and how it was defined. Well, you take the tuple of matrices A and B, so those are vectors, matrices are vectors, right? And then you just send it to what? To the sum of diagonal entries of the trace of the following matrix, the conjugate transposed of B times A. Okay. Now, what is nice about this Hermitian form is that indeed it satisfies condition 3. So it is indeed the inner product. It is indeed one of those examples of inner products. And well, this example has its name. I mean, whenever you deal with such an inner product defined for matrices, I mean, this one, this is a so-called Frobenius inner product. Again, so we have 3 examples, right? The basic one is a standard one, so it's this one. Now there's the example which deals with the integral, okay? And then there's this example which deals with matrices, which gives us the so-called Frobenius inner product. Okay. By the way, of course, well, let me mention a couple of non-examples. As I mentioned last time, if you just take, say, a trivial 0 Hermitian form, say h of xy is just set to be 0 for all x and y. This is, of course, Hermitian, right? But it is not an inner product, but it is not the inner product. because precisely the point here is that the condition 3 fails in this case, right? Look, I mean, again, at the condition 3, what does it tell us? Well, it tells us if we apply our form to the non-zero vector, we must get something non-zero, actually strictly positive. But this is, of course, not the case for the 0 form, because you will get 0 always. Right? So this is clearly non-Hermitian. Okay, so now, well, let me, is there any question before I'm going to the next step? Is there any question? Questions so far? Okay, so now let me deduce, let me sort of state and prove a couple of properties of inner product spaces. Remember that what's the inner product space? It's a vector space together with an inner product, right? Okay, so here the first definition we would like to state. So let V be an inner product space for each vector V from V. We define the norm or equivalently one can call it length of V by the following formula. So basically, well, the notation is like this. I put this double vertical lines of which kind of brackets, double brackets, okay? And then, so this is a notation for the norm or the length. And this is just set to be, you may guess what's that? So it's a square root taken from the value of the respective inner product on the vector V. So it's V, comma V. Well, recall that by property 3, by the property 3, this value is always strictly positive if applied to a non-zero vector, right? So it makes sense to take a square root. Okay. Yeah, so this is a length. And now, well, for instance, well, we just look at the following. So in the case of the standard inner product, what's the length of this vector? We'll say V1 to Vn, this complex coordinates V1 to Vn. Well, this is clearly the square root, right? Of what? Of the sum from y to n of the complex number Vi times Vi bar times its conjugate, so meaning that I have to put here Vi, absolute value of this complex number, square of the absolute value. Right? So that's a formula. So let me mention that Vi square is just Vi times Vi bar for each I. So since this is an example of the length for the standard inner product, well, it has a name, so this length is called the standard norm, or length. Sometimes the word standard is replaced by the word Euclidean. So it's either called a standard norm or Euclidean norm. Okay. Of course, again, I mean, we have a different kind of norms now, right? So whenever you have, say, an inner product space, for instance, you can look at this complex valued function space, right? And then you have this inner product defined by means of the integral, right? That I mentioned right here. So this one. Yeah, this one. Then, well, you have the notion of the length of the norm, right? For instance, in this case, what's the norm of the function f? Well, it's just this one. just square root of the value of the respective integral, right? And this is the norm of f. And of course, one can do the same for matrices as well. So there's a Frobenius norm, right? And this is again defined in the similar way. So you just, so what's the norm of the matrix? Well, just the square root of A comma A, right? Okay. So, right, so we get a bunch of examples of norms, of lengths. Now, well, there's a following lemma, the following fundamental property lemma. So again, so let V be an inner product space over F, over field F. Okay, so here one should mention that F is either R or C. Right, again, I mean, so far I define the inner product over C, but of course you can just restrict yourself to R, because R is a subset of C, right? And I mean, all the properties, they're actually valid. And just restrict yourself to R. And this is a so-called real inner product. So you also will get the norm, in this case, the length, and so on, right? Everything will be the same. The only difference is that over R is just kind of smaller, right? Okay, so okay, so right, so what we have here is we have an inner product space, either over R or over C. Then what is claimed is that for all vectors V and U from V, and any scalar C from F, we have the following properties. One, if you want to compute the length or the norm of the scalar multiple of a vector, then this is clearly the absolute value of C times the norm of V. Again, what is the absolute value of C? Of course, it depends on whether you are in the real numbers or complex numbers, right? Real numbers is just the standard usual absolute value, and over complex numbers, it's just the sum of squares of coordinates, square root of the sum of squares of coordinates. Okay. Second, well, the norm of V is always greater or equal than 0. That's clear, right? And third, well, the norm of V is 0 if and only if the vector is 0. And that's also clear, right? And that's also clear. Okay. So, right, so now let me state and prove the following pretty famous inequality that has different names and reincarnations. Well, in this setup, it's called Cauchy-Schwarz inequality. Let me stress that this is indeed stated, and this holds for any inner product space, for instance, for matrices, for functions, for usual complex numbers, or even real valued functions, or for usual dot product, right, etc. So, so it's a very general inequality. So it's stated as follows. So let V be an inner product space over F. So here F is either R or C. Then for all V and U, from V we have the following inequality. So let's just look at the inner product and compute it of these vectors. So this way we will get either real or complex number, depending on where your field is. And then we'll just take the absolute value. Okay? And then on the right-hand side, we just take the product of length of these two vectors. in this vector space with respect to that inner product. And then the claim is that the left-hand side is always less or equal than the right-hand side. So let me prove this. Okay, so, well, there's of course particular case. So if one of those vectors is 0, say u, well, doesn't really matter if v is the same argument. Of course, if one of them is 0, then the result is immediate because both the left and the right-hand side are just trivial, right? Then it's okay. So we may assume that u, both vectors, are non-zero. So now for any, well, let's just take any scalar. For any scalar C from our field, what do we have? Well, we just have the chain of the following inequalities. So first of all, well, clearly 0, well, I mean, clearly this number, I mean, if you just take the square of the length of this vector minus cu is always greater or equal than 0, right? Because that's a length. And now you take a square, because it's positive, not negative, right? So that's obviously true. Now what we do, let's just expand it using the definition, because the square of the length, let me remind you, this was just defined to be this inner product of v minus u with itself. Maybe I should put arrows, right? And then what we can do, we can use the properties of the Hermitian form of the inner product. Because remember, this is linear with respect to the first coordinate, to the first factor. And this is, and then this is almost linear with respect to the second, well, we have to put a bar, right? If you move out the constant. So, okay, let me carefully expand it. So, okay, so here I want to expand it with respect to the first coordinate. So what's this? This will give me v, comma, the second coordinate stays minus c times u, comma, v minus the second coordinate stays. Okay. Again, here I use the fact that my form is linear with respect to the first coordinate. And now, well, I want to expand it with respect to the second coordinate, but here I have to be careful, right? Because whenever I move out the constant, it has to come with a bar. Okay. So let me do it. So v, I just expand this expression, v comma v minus, and now what do I have? I have to move out this c, and it comes with a bar, v comma u, minus, now I do the same for the second summand. So now c times u v plus, right? So c times c bar, so this c bar of u comma u, right? Again, and this holds for any scalar c. This inequality holds for any scalar c. Okay, so now take c to be a particular scalar. So you take c to be this fraction. I mean, you just take the your inner product on these vectors divided. So that's a number, complex number, right? Real numbers divided by this one, u comma u. So that's a number. So take c to be this number. Okay, and then substitute. Substitute in this inequality. Okay, what do we get? We get 0 less or equal than what? Okay, let's just substitute and see what will happen. Okay, this summand stays v comma v. Then minus, what is c bar? Okay, so instead of this summand, what do we get? We get v comma u over u comma u bar, right? Because that's this c of what? Of v comma u. Now minus, well, the same thing. Okay, so v u over u without bar, right, times the same number, u comma v, like this, okay, right? And then finally, what do I have here? Plus c times c bar, what's that? Well, it's just the, okay, it's just square of the length of c, right? And what's this? So basically, we can write it, c times c bar is just c square, right? So basically here just write v comma u over u comma u square, right, times u comma u. And what do we see? Well, we see that indeed something will cancel, right? Something will cancel. So what do we get? Well, we get actually that this part, if you look carefully what is written here, this part will reduce to the following expression. So just v comma v okay. Now, let's just look here. So indeed, what will happen here is that, okay, so this will be, right, okay, so let me write it, minus u comma v times v comma u over u comma u. Here, of course, one uses the second property of the Hermitian product, right? For instance, if you have a bar of v comma u, I can just substitute by u comma v, right? By u comma v. And then I'll see that, so here what I will get, I'll just get, okay, so let me do it. So, right, so this will be replaced by u comma v, right, this one. And then see that this term is the same as this term. So this term then will become the same as this term, right? So meaning that this is just 2 times this term, right? But then look at this term. This term is just the same as this one. So minus 2 plus 1 is minus 1. So, and that's what is written here. Okay. And then finally, well, what's this? What is written here is just v comma v. Well, minus, now just write it carefully, of v comma u square, because that's what it is, right? Because look, again, we apply the second property. So this v comma u is just u comma v bar. And the complex number times its conjugate gives us the square of its absolute value, and that's what is written here, divided by u comma u. Okay, so that's a small trick. And of course, well, if you look carefully what is written here, well, what we can do now, well, let's just move this number to the left-hand side and multiply both sides of this inequality by u comma u. Your form applied to u comma u. Then what we will get? We will get the desired Cauchy-Schwarz inequality. Yeah. Okay, so let me write it. So of course we get this. Right? And then after multiplying both sides of this inequality, we get this. Don't forget that we multiply by a positive number, so inequality stays. And then finally we are finished. Well, now just take the square roots of both sides, and we are finished. Right? Okay, so that's a Cauchy-Schwarz inequality. You have seen it probably many times in the calculus class under maybe different names. Well, let me just give you an example. For instance, let's apply this inequality to complex valued functions and to this inner product. Ft gt bar. What do you get if you apply to? Well, it just stated, okay, so, well, what do we get in this case? Well, what is this VU? Okay, so maybe FG. What is the absolute value of this inner product? Well, that's clearly just 1 over 2 pi, right, of the absolute value of this integral. Okay, now what is length? What is the length of? Well, we also know that this is what? This is just 1 over 2 pi, right? And then what we have to do, we'll just need to take, okay, maybe I write it. So it's just the square root of f comma f, right? Yes, so and that's clear that this is just, well, so here we just need to substitute and we will get the respective integral, right? Okay, maybe I write it. It's the square root of 1 over 2 pi of the integral from 0 to 2 pi of ft squared. And respectively for g comma g, we get the square root of this integral, right? Now we can combine all these integrals together and get the following inequality. Of course, this 1 over 2 pi will cancel because there are 2 square roots and we need to multiply them, right? So basically you can forget about 1 over 2 pi. So basically what, okay, we will end up with the following inequality. This integral, the absolute value of this integral has to be less or equal than the product of those values. And perhaps you have seen this formula in the calculus class. Well, at least if you were taking in the second calculus, there should be something like this. Okay, so that's a Cauchy-Schwarz inequality. Now let me mention another inequality, which is actually a consequence of this Cauchy-Schwarz. So let me mention the following corollary. This is the so-called triangle inequality. And what this states is that whenever you are given an inner product space over R or C, then for all vectors, we have the following. V plus U, the length of the sum is less or equal than the product, than the sum of length. Again, let me stress that this length is a general length, right? So it's a square root of the value of your inner product on the vector V, right? And well, let me prove this. Well, to prove this, we again use a definition. So what's, well, let's just look at the square of the sum, of the length of the sum. By the very definition, this is just your inner product applied to this vector, to the sum, right? And then what we can do, we can again expand it. So it's the same trick, just expand it. So we get V comma V plus U comma V plus V comma U plus u comma u. Just use the properties of the Hermitian form or symmetric bilinear form. And then, well, again, we just use, so what is v comma v? Well, it's just a sum of the, it's just a square of the length, right? Plus, now one has to be a little bit careful here. Okay, so what is this? This is, look, I mean, this is z. If it's z, then this is z bar, right? And z plus z bar, it's a property of the complex numbers. Let me put it here. Z plus z bar, what's that? This is always a real number. This is 2 times the real part of z, which is 8, right? Okay, so one can write it like down. So 2 times the real part of this complex number. Plus, of course, this u comma u, which is just the square of the length of u. Well, but okay, but clearly, I mean, this one is less or equal than, we'll just keep the first summand, but then we replace the middle one by 2 times the absolute value of uv. This is obviously greater, right? Greater or equal than this one, because, well, here we're just dealing with the real part, right? But here just replace it by all the absolute values. So it's easy to see that it's definitely greater, and then we just keep it writing down here. Okay. But now what we can do, we can just apply the Cauchy-Schwarz, Cauchy-Schwarz to the middle term. So what do we get? Get less or equal, then v, again, we just keep it, square, plus. Now here we have 2 times the product of lengths, right? Plus u squared. And then we all see that what is written here on the right is just a formula for the square of the sum, right? So it's just what? It's just v plus u squared. And then, well, to get the triangle inequality, we just need to take the square roots. And that's finished. Okay, so that was a proof. Now again, you can use this triangle inequality to get many nice inequalities. If you just substitute your favorite inner product space, you get one. Okay, so that's okay, right. Again, so what I would like to do, I would like to fix an inner product space. So product vector space V together with some inner product. That's an inner product on V. Okay, so this is an inner product space. And again, I mean, this all happening either over R or C, doesn't matter. So over these 2 fields. So the first thing we would like to introduce is the concept of orthogonality. And so here, so this is, so vectors, say V and U from V are called orthogonal. With respect to this inner product if, well, if one may suspect what's that, if you just compute this inner product, these 2 vectors, and one gets 0. And this is the standard definition, right? Like in the first year linear algebra, 2 vectors are orthogonal if and only if the dot product is 0. And dot product is an example of an inner product over real numbers. Okay, so now the second concept is just an extension of this one. And again, you have seen it before, maybe a little bit under different name or a little bit rephrased in the first year linear algebra. So a subset S of the vector space V is called orthogonal. Well, if any two distinct vectors, orthonormal well, if S is orthogonal and at the same time consists entirely of unit vectors. Okay, so let me give an example. So several concepts would like to see how it works. Okay, let me give the following example. Again, I will take this vector space of complex valued functions, continuous complex valued functions on that interval from 0 to 2 pi. And let's take this inner product, this function inner product, 1 over 2 pi, from 0 to 2 pi of ft gt bar dt. So take this inner product on the vector space, this infinite dimensional vector space. Now, well, for any integer n, let's just look at the following function. So let me denote it by f over index n of t, and let's just set it to be the following. So I take the exponential function, okay, to the power I n t. What's this? By the way, one has to be careful. Okay, let me first write where t is from this interval. Okay. So now this notation, well, beware that this notation, so what is I n t? E to the power I times something. What's that? This is a complex valued function, right? As you remember from the calculus class, this is what? This is cosine of nt plus I times the sine of nt. That's what it is, right? So you put here, you put this number here and here. So e to the power I times some number is precisely cosine of this number plus I times sine of this number. That's a notation for this complex valued function. Okay. So again, what do we have so far? We have this vector space of all continuous complex valued functions on that interval. And then we just chosen a subspace inside, okay? So S, which is just the subset inside, which consists of all these Fn's. By the way, n can be negative, right, as well. We can easily substitute n to be a negative number, and this will still make sense, right? It's a particular function. So the claim is that S, this subset, this infinite subset, is an orthonormal subset, orthonormal set, with respect to that inner product here. Okay. Well, basically, why is it so? Well, okay. So let me. Right. Okay. Let me actually leave it as an exercise, because what one has to check right? To show, in order to show that this is an orthonormal subset, well, you have to show two things. Just give you a hint how to do it. First of all, you need to show that each inner product. So first, we need to show that Fn, Fm is 0 if n is not m, right? This will tell you that this set is orthogonal. And then you just need to show that if you try to compute this, then it's always 1 for each n. And this condition will tell you that this set is orthonormal for each n. And again, well, you just substitute it inside that integral and do some computations with exponential functions, which is pretty easy, right? Okay. So this example shows that orthonormal subsets, I mean, they can be sort of infinite, right? And then, I mean, we can deal with functions, right, as well. So it's, all this totally makes sense. Okay, and what also makes sense is the following definition. Well, a subset of that vector space V is called an orthonormal basis with respect to the chosen inner product if it is, at the same time, it is an ordered basis yeah, so meaning that it spans the whole vector space and it is linearly independent, yeah, and that is orthonormal. That is orthonormal with respect to that inner product. Yeah? So again, what is orthonormal basis? It's a basis which is orthonormal with respect to that inner product. Okay. So let me mention, of course, a bunch of examples. First of all, you can look at Fn, where F is either R or C, right? And you can just look at the standard inner product, standard. Then, well, the standard basis, we can choose a standard basis of Fn, which the one consists of zeros and ones. Yeah? You just put 1 at the position height. This standard basis is orthonormal with respect to this standard inner product. Okay, so indeed, it's very interesting question. It's a very interesting question, whether one can find an orthonormal basis of this space, of this infinite dimensional space, of all complex valued functions, or real valued functions. Right? That's a really interesting question. Okay, we will actually, yeah, I'll try to address it later on. Okay. So there's one candidate, it says, however, one has to be a little bit careful here, right? Because, for instance, it's not clear whether it spans the whole space, right? Yes, exactly. That is related with Fourier series, right? That's how the Fourier series appear, indeed. So indeed, that and that's what it means, right? Basically, all this Fourier decomposition means that you basically choose an orthonormal basis inside that function space, and then you just take your function, a vector, and write it down in terms of that basis. And the coefficients are precisely the Fourier coefficients, right? Okay, whatever. So Okay, so that's was a story about the basis.